Hello everybody. In this video we will talk about the U-substitution method and definite integrals. This should complete our discussion of this technique, and after practicing with homework examples, you will be able to apply this method to many other problems, not just the ones that we've discussed in this class. So let's take a look at the first problem. We have the integral from 0 to 1 of 3x cubed over the quantity 2x to the fourth plus 3 raised to the third power. Let's take a look at the first step. The first step is just like before. We need to identify the expression of x that we're going to substitute with u. In this case, it's going to be 2x to the fourth plus 3. Next, we differentiate each side of this equation. So we get 8x cubed dx on the left, and on the right we get 1 du. Okay, now we'll look at the integrand. There we have 3x cubed dx, which means we need to multiply each side of this equation by 3 over 8, and that will give us the expression that we have in the integral. So we have 3x cubed dx equals to 3 over 8 du. All right, so now we have everything that we need to know and we need to have to replace our expressions of x with u. But one step that we need to do is take care of the limits. So how do we go about that? So limits. Now recall that u is defined to be 2x to the fourth plus 3. So for the lower limit, if x is equal to 0, u is going to be 2 times 0 to the fourth plus 3. And that, of course, is just 3. So this is our new value for the low limit. Okay. What about the upper limit of integration? So x is equal to 1. Then u is 2 times 1 to the fourth plus 3. And that gives us 5. Okay, so that's the upper limit. And now we have everything that we need to convert our integral into a new variable. So let's see what that looks like. So now we have the integral from 3 to 5, new limits of integration. And what is the constant here? That's going to be 3 over 8 u raised to the negative third du. Okay, much simpler integrand, new limits. All right, let's go ahead and compute the antiderivative. So this is going to be 3 over 8 times u to what power? We do negative 3 plus 1. That's negative 2, which means we need to divide by negative 2. And we evaluate it from 3 to 5. Okay, let's go ahead and compute this value. So the constant here is negative 3 over 16. And we are evaluating u raised to the negative second power from 3 to 5. Okay, let's write out all the steps. So this becomes what? At 5, this is going to be 1 over 25. And at 3, that's 1 over 9. And this expression, just plug that into your calculator. So what do we get? Negative 3 over 16 times negative 16 over 225. And once you simplify this, it turns out to be 1 over 75. Okay, that's the answer. So notice what we've done. The first step was the same. We found out what our expression in terms of x is for u, did the differentiation, and then took care of the limits. All right. Now, alternatively, I would like to give you another way of computing the final answer without taking care of the limits. So what else can you do? So let's say I did not convert my limits. Okay, so let's say I want to stick with x is equal to 0 and x is equal to 1. You can do that as long as you also convert your antiderivative back to the original variable. So what do I mean by that? So negative 3 over 16 times, and what is my antiderivative? It's u to the negative second power. So now I'm going to plug this back in, 2x to the fourth plus 3 raised to the negative second power. And now I'm using the original limits. Okay, what were they? 0 to 1. I can do that, and you will notice that the answer will be exactly the same. So let's go ahead and compute that. Let's see what happens. So we get 1 over 2 times 1 to the fourth plus 3 squared minus 1 over 2 times 0 to the fourth plus 3 squared. Okay, and notice that it will give us exactly the same answer. Not surprisingly, because that is how we computed those limits to begin with. So this is going to be negative 3 over 16 times this difference right here. And that's, of course, exactly the same as 1 over 75. Okay, so what is the point of this way? The point that I'm trying to make here is that you can convert the limits and stick with the u function, or you can go back to the original expression of x and stick to the original limits, but we cannot mix them up. Okay, that is, if you're going to evaluate this expression right here, then it needs to have the u limits, the new limits. If you're going to evaluate this expression right here in terms of x, then you must use the old limits. Okay, so that's what we do when we have a U-substitution method and definite integrals. All right, let's go ahead and take a look at one more example. Here we're working with the trig function. It might look a little bit busy, but once we work out all the details, you will see that the integral is fairly straightforward. Okay, what is our first step? We need to identify our u function. Well, I'm inspecting this integral and I notice that I have secant squared, and I know that the derivative of tangent is secant squared. So I'm going to say tangent of 3x squared, that's going to be u. Okay, now I differentiate each side of this equation, keeping in mind that I need to apply chain rule. So the derivative of tangent, that's secant squared 3x squared, times the derivative of the argument, and that's 6x dx. Okay, and then on the right we just get 1 du. All right, so what do we do now? We have 3x over here dx and secant squared 3x squared. Okay, but over here we have 6x, so we need to divide everything by 2. Now we have 3x secant squared 3x squared dx is equal to 1/2 du. Okay. All right, so we have everything we need for the integrand. What about the limits? Let's go ahead and convert the limits. We have the old limits, we would like to compute the new ones. So u is defined as tangent of 3x squared. So when x is 0, what happens to u? U is tangent of 3 times 0 squared. So tangent of 0 is 0. Okay. What about the upper limit? So x is equal to root of pi over 12. That means u is equal to tangent of 3 times root of pi over 12 squared. That's just pi over 12. And this is tangent of pi over 4. And that's a nice number. That's 1. Okay, so now let's convert this integral in the new variable. What is that going to be? So the integral with new limits, that's going to be from 0 to 1. Okay, and what is the integrand? Well, let's see. This is our expression for 3x secant squared 3x squared dx. And we have tangent equals to u. So we have u cubed times 1/2 du. And notice how simple this integral is. Okay, so we can evaluate this fairly easily. So 1/2 times u raised to the 4th power, and we need to divide by 4. We evaluate this from 0 to 1. So this is 1/8 times 1 to the 4th minus 0 to the 4th. And that's, of course, just equal to 1/8. Okay, and that's it. That's all we need to do to compute this integral. So notice the original expression was kind of messy, lots of stuff going on, but once you untangle all of those components and rewrite everything in terms of a new variable, you'll see that the integral is rather simple. All right, so we've covered the method and how to apply it. We talked about various functions and how to look for patterns where you see that you have an inner function and an outer function, and you have a constant multiple of the derivative. So you've seen how this method is applied. I want to make a note that if you go to Calculus 2, this method will be used heavily. So I encourage you to really try and master your skills in applying this method, as it is one of the most commonly used technique in the entire course. All right, thank you all for watching. I will talk to you next time.